today we are joined not by one, not by two, but by three speakers who will guide us through how to achieve hard real-time performance with Linux-based systems. So first of all, we have Catherine. She's from Texas Instruments, and she will introduce us to the hardware perspective and TI's approach to hard real-time. Then we have Nick Freudel from Phytec, and he will go into more details about how to actually make it work on your SOM hardware. And then we have finally Dominic from IBV. He will dive deeper into industrial protocols and hard real-time. So you don't want to miss that part, right? And without any further ado, let's get started with Catherine.
Everyone, thank you, Richard, for that introduction. I will get started by sharing my screen. All right, so at TI, we have developed a multi-protocol solution that targets three main market sectors: PLCs, industrial and collaborative robots, and single and multi-axis motor control. One of the biggest advantages of our approach is that you can run multiple industrial protocols with the same hardware design. So by simply loading different firmware images, you can switch between protocols during boot time. And in addition, our hardware is ready for gigabit protocols, including TSN. And another value is that we offer a single chip solution for field bus communications. This allows you to integrate sensor and actuator and gateway applications, and even add services such as web services or remote monitoring. And lastly, we provide a one-stop shop where we are your main contact for both SoC and protocol-related aspects of your product, simplifying your development and support. And all in all, with our multi-protocol approach, you can enjoy flexibility, scalability, and reduced time to market for your industrial products. And so on the next slide, here we go. On the next slide, I'll be talking about the AM64, which is the processor that's on the 5-word. And this processor has up to 853 ARM cores at a clock speed of up to gigahertz, but of up to 1 gigahertz, and up to 4 R5F real-time cores with a clock speed of up to 800 megahertz. This SoC is equipped with an ICSSG, which we use to run the industrial communication protocols on. ICSSG stands for Industrial Communication Subsystem, and one subsystem has 6 PRUs, which stands for Programmable Real-Time Unit. This is a small RISC processor that can do very accurate timing, and you can implement low-level protocols like EtherCAT and Profinet on the PRU. And then higher level protocols are typically implemented on the R5F core. This processor, you can use up to 5 gigabit Ethernet ports, and 2 of those are 2-port gigabit Ethernet switches with TSN capabilities. The AM64 also supports multi-axis motor control. It houses up to 12 multi-protocol position encoders and up to 36 on-chip Sigma Delta filters. This processor is also compatible with the AM243 MCU in our portfolio, which has all the same features, but no 853 cores. So this would be good for non-Linux applications if that is of interest. And so now that I briefly talked about TI's offerings and the AM64 processor, Nick can take it away on his portion of the presentation.
All right, thank you, Catherine. I just want to make a small introduction of myself. My name is Nick Freudel. I'm a product manager at Phytec. We are an embedded system developer and manufacturer with our own production in Germany. And we have roughly around 400 employees in 5 different countries around the world. I'm just going to start with a small introduction of our core product, our system and modules. I'll just make a small explanation about it, because maybe we have also people here in this webinar which are not that deep into embedded stuff like normally in our webinars. A system or module, or short, a SOM, is actually a compact, small, little embedded computer. It has all necessary CPU circuits on it, which you need to get the CPU boot. For example, the CPU power management, where you need highly precise voltages at the CPU. We implement the RAM circuits, which are really time-critical circuits where you need a lot of experience. Our SOMs offers the eMMC and an Ethernet PHY. So with a SOM, we already took care about all the time-critical control signals that you actually don't want to care about. And with this, we take the most complex part away of your design, of your device at the end. If you're using a SOM, this really makes your carrier board design much more easier, cheaper, and faster. To make this clear, I just wrote some numbers down that, for example, our SOMs PCB has around 12 to 14 PCB layers, where a carrier board, when you're using a SOM, probably just needs around 6 to 8 PCB layers. This shows that this a SOM design makes it much easier for your carrier board design. Coming to the AM64 processor from Texas Instruments, we designed a SOM around it. We are calling them the FICO AM64 SOM. And you have two connectors on the bottom side of the SOM where you have all CPU interfaces available. We also designed a carrier board around it, calling it Electra, where you also have all the interfaces and connectors available you need to use actually the processor, like, for example, the RJ45 connectors for Ethernet or USB for debugging and so on. And the most important part regarding this webinar, we have the PRUs, the programmable real-time units, accessible on this board via an adapter. I will come later back to this. I will make just a short break because maybe we have people which already worked with our hardware and software, and they are now asking, because we already talked a lot about PRUs, why you should use the PRUs and not a software-based approach with a real-time Linux kernel. Because Linux kernel above version 6.12 has a real-time support with cycle times about 10 to 100 microseconds. And then it really depends on what your application, how your application defines the word of real-time. If you really have a hard real-time scenario, like using EtherCAT or safety critical applications, where you have a strict timing and real-time requirements, then you probably use a CPU where you have PRUs, because then you can make sure that you have real hard real-time. If you have an application where you probably are going using soft real-time, for example, an HMI touch interface, where you not really have a hard real-time requirement, then a software-based approach could work. And now we talked a lot about the AM64 and the PRUs. I just want to present you something we created together with IBV that will help you using the PRUs and the AM64 together. We are calling it the FICO AM64 Industrial Communication Kit. It's an all-in-one kit for real-time applications where you can use EtherCAT, PROFIBUS, and Ethernet IP directly on the AM64 board. You will get this kit with all cables you need, with all power supplies and so on. So you can right start your developing with this board. You get the SDK from IBV to use EtherCAT, PROFIBUS, and Ethernet IP together with our Yocto BSP. You will have demo application you can run out of the box directly when you receive the boards. You will get a quick start guide, which really makes you step-by-step guide how to start the board, how to start the demos, and so on. And you have 5 Ethernet ports available on the boards because you have 310 gigabit available on the board itself, and you get the adapter PCBs with 2 additional Ethernet ports where you can access the PRUs for real-time applications. This kit is now available on our website at phytec.de. With this, I want to thank you for your attention and turn it over to Dominik from IBV, who will talk a little bit more in detail about the SDK they created for our board and the communications protocol.
Thank you very much, Nick. Hello, everyone. I would like to introduce myself briefly. Dominic Rath, and I'm head of technology at IBV. We are a software development services company with a lot of experience in industrial field bus communication, industrial Ethernet, real-time application development in general. You can get the slides afterwards so you can read the details for yourself. About the agenda, I would like to tell you something about requirements for industrial Ethernet devices. Why do you have real-time requirements in that? Then something about how you could implement industrial Ethernet devices for EtherCAT sub-device, PROFINET device, or Ethernet IP adapter. A little bit about the protocols, hardware and software architecture, what features we and TI and Phytec support, and a live demo of the SDK that we built together. I will tell you something about the industrial Ethernet SDK, which is what Nick just presented to you. So it's the hardware and the software part. And then I can tell you a little bit about possible use cases, how you could use the Fireboard AM64 with the industrial Ethernet SDK to build the different products, different ideas. Hardware and software requirement. Okay, yeah, good point. I should share my screen. Sorry. Hardware and software requirements for industrial Ethernet devices. With regular networking stacks and Ethernet MACs for TCP/IP communication, like you know from your laptop and also from an IPC running Linux, they are typically optimized for bandwidth and throughput, but not for real-time communication and low latency. Industrial Ethernet communication on the lowest layer uses standard Ethernet 802.3 for the data transfer, but it comes with real-time requirements both in the controller and in the device and in the communication from the controller to the device. You might be facing different requirements in controlling nodes and in the I/O nodes. One example that I could present to you is an EtherCAT sub-device. In an EtherCAT sub-device, the master sends out an Ethernet frame, and that frame travels through all the slaves, and each slave takes out the outputs that are meant for this slave. And on the fly, it places all the inputs that it collected in this cycle and puts them in the frame, and the frame passes through the network. And EtherCAT typically uses 100 megabit Ethernet. So this frame is between 5 and 120 microseconds long. So you really have very tight real-time requirements. The frame itself is only a few microseconds long, and it passes from the input of the slave to the output of the slave in nanoseconds, a couple hundred nanoseconds. With the PHYs, you get maybe a microsecond delay for each slave. And you need to take the data out and put new data in the frame while it passes through. And that's where the tight real-time requirements come in the EtherCAT network. And in addition, you typically want the freshest input values from your slave. And you also want to use the output values as soon as possible after the frame went through. So that's where you get the tight real-time requirements. Another example is the whole TSN protocol family with time-triggered send or some variant of that. You typically have very strong timing constraints when sending your industrial Ethernet frames, and some Ethernet MACs make that easier by supporting time-triggered send, or TSN. That's also called the 802.1 QBV enhancements for scheduled traffic or time-sensitive scheduling. These are means to schedule your traffic on your Ethernet network. But today we will be looking into EtherCAT, PROFINET, and Ethernet IP. Brief overview over EtherCAT. EtherCAT uses a logical line topology, so all of your slaves are connected in one line. But physically, you can connect stars and trees, and you can have branch lines. That's all possible with EtherCAT. You have one main device and up to 64,000 sub-devices. And you have mostly the cyclic communication. That's what you care about. You want to transfer data in real time, and you have reserved bandwidth for each of your sub-devices. We transfer the so-called PDOs, process data objects, and the cycle times on your EtherCAT network are up to 20 kilohertz, sometimes even higher, most likely a little bit below that, so most likely 100, 200 microseconds or so. But that means you need to act on input and output at much faster. So you want to act on your input in microseconds. And that's something that you can't do with the standard Linux, not even with the real-time patch. Communication principle of EtherCAT, you update all your IOs of all the sub-devices with one or a few frames if you have a very large network. And then you can have acyclic communication for non-real-time data in the background that doesn't affect the real-time critical traffic. And for that, EtherCAT offers mailbox communication that can open over EtherCAT, Ethernet over EtherCAT, or the file transfer over EtherCAT protocol. You have network supervision and diagnosis, so you know what's going on in your network, if a slave is up or down. And you have time synchronization, the so-called EtherCAT distributed clocks feature that allows you to synchronize time between your main device and all of your sub-devices to below 100 nanoseconds. I think they claim a microsecond, but in reality, you get more like 100 nanoseconds. And that allows you to do, for example, synchronized latching of IOs in your sub-devices across your factory floor, or synchronized toggling of outputs on both ends of your factory floor down to microseconds. How could you develop an EtherCAT sub-device with the TI AM64 and on the PHY board AM64? You use the PHY board, you use the Linux BSP coming from Phytec. On the R5F cores, these are the 800 megahertz real-time cores. We use the Industrial Communications SDK from TI and the TI AM64x SDK. In the PRU ICSSG, we use the EtherCAT slave firmware, the EtherCAT slave controller. And then you get the EtherCAT network on the 2 PHY ports. And then we have our Industrial Ethernet SDK that we developed together with Phytec. You use Beckhoff's slave stack code tool and the Beckhoff slave stack code, ET9300. You put in your custom object definition that defines, okay, I have these many inputs, these outputs, and they have the structure and variable size and so on. And out you get the ESI file, the EtherCAT subdevice information file, and you get some source code that gets compiled together with the slave stack source code, and then runs on the R5F that includes the object dictionary and the slave information interface. And then you build your custom EtherCAT subdevice application, for which you get an example from us in source code that does the PDO handling of your IOs and that does the state handling and so on. And then we have an RP message server that communicates from the R5F with the Cortex A53 core, where the RP message client runs. And we have a custom Linux application that you also get in source code that maintains the EtherCAT state and that allows you to transfer process data objects from and to Linux with the real-time capabilities that Linux can support, while your R5F continues to run at the full speed, and the PRU runs at an even higher speed and handles the frames passing in and out in nanosecond delays. The architecture for this, we are using the TI AM64 PRU ICSSG and TI's EtherCAT firmware, which is an EtherCAT slave, EtherCAT subdevice controller, ESC, that manages the 2 EtherCAT ports and includes all the frame processing and forwarding and stuff. TI supports 2 protocol stacks, the EtherCAT slave stack code. This is the one that we are using in the Ethernet, Industrial Ethernet SDK. They also have their own EtherCAT subdevice stack that is based on the ET9300, which we are not considering here because the slave stack code provides us with more flexibility. And that's what you get in the Phytec SDK. For this, I can show you a demo that is running on a 5-core AM64 system on module with the Linux BSP and the R5F application and the PRUs and some IOs. And then we have another Phytec board running our EtherCAT master stack. That's an IBV product that you can license from IBV. You can use whatever EtherCAT main device you want. With our software, you also get a configuration tool, the EtherCAT configuration library, and the UI for this. We have our ESI file that describes what this sub-device looks like, and we do an online network scan. We find our sub-device, and then we configure the network, transfer that to the EtherCAT main device, and then we have a working EtherCAT network. For that, I will show you this. So for this part of the presentation, we are up here. This is the PHYboard AM64 running the EtherCAT sub-device application. This is the PHYboard running the IBV EtherCAT master stack. And we have the IBV configuration tool. And I can do a network scan. And now I'm scanning. This is running, the UI is running on Windows. It's talking to the main device Linux, and it's telling that to scan. And we use the found devices, the PHYboard Electra, so that's the AM64 board. We can change the cycle time because we can do that on this version down to 125 microseconds. And then I can transfer the resulting ENI, the EtherCAT network configuration, to the target, and I tell it to link it so that it's already in use. And then our master stack is up and running. We see some key performance numbers like the frame jitter and stuff. And we get access to our I/O variables. This monitor runs on Windows and talks with the main device via normal Ethernet, so TCP/IP based. And then we can, for example, go to our motor. And I should show you the camera for that. So this is this motor that's controlled by this variable. And I set the speed to 55 and the motor starts turning. Additionally, because we have not only the R5F application and the PRU firmware, we also have a full-featured Linux on the other end. We also have an example application running on Linux, and that allows you to transfer process data to Linux and from Linux. So we have some process data that's coming from Linux, and I can increment with the letter A. I can increment this counter here, and we can see on the master monitor that the master is receiving this data right away. The same thing I can do with outputs. I put in the number 1, 2, 3, 4 here, and the process data out that comes from the main device to the slave to Linux, and we see the data here. So that allows you to transfer process data objects, PRU, R5F to Linux. Yes. Okay. So much for EtherCAT. The beauty of TI's solution is that you can also have a Profinet device that looks pretty much the same based on the TI AM64 and the PHYboard. Again, we have the A53 running the Linux BSP. We have the Industrial Comms SDK. We have the Profinet device firmware. We have the TI Profinet device stack. We have the Phytec Industrial Ethernet SDK that you get from IBV and Phytec. We have our custom Profinet application running the R5F, running on the R5F. For Profinet, you use GSDML files that describe what your device looks like, pretty much the same as the ESI in the EtherCAT case. And this time we have 2 RP message servers, one for the PDOs, just like before, and then another for the non-volatile memory that the Profinet stack requires. And we store that non-volatile data on the Linux file system just because it's easier to do that way with Linux. Yeah? So you can package everything on your Linux file system where you have all the freedom that you would like, and you don't have to care about MCU programming. The architecture is pretty much the same as before. We use the PRU ICSG and TI's Profinet device stack. The Profinet device stack supports all the conformance classes A, B, and C. So not D yet, so no TSN yet, but all the traditional Profinet conformance classes. Minimum cycle time is 250 microseconds. It is a 100 megabit 2-port cut-through switch. It supports isochronous mode, media redundancy protocol, and more. Have a look at the TI documentation when you get the slides. For this, we've also prepared a demo. with the Profinet device running on a Phyboard AM64 and the controller running on a CodeSys soft PLC running on a Linux PC. And for that, I use this setup. So now we are looking at this Phyboard AM64, hardware-wise exactly the same as the one above. And we are looking at this silver IPC, where the CodeSys soft PLC is running. And we have the Windows PC, where the CodeSys engineering tool is running. And we already see some variables toggling in the Profinet application, PN. And there's a potentiometer here. And if I turn that potentiometer, you can see the numbers change in this variable. So we really are seeing live data. We also have exactly the same Linux application that also outputs data from Linux via Profinet back to the PLC running on the silver PC. And because it's easier right now, we have the same again for Ethernet IP, yet another protocol, yet another hardware, just another R5F firmware. And we can do the same. We have another potentiometer down here. And if I turn that potentiometer, you can see that the live values are changing. Values are from this potentiometer to the Ethernet IP adapter device, and then to the soft PLC. And the soft PLC talks with my Windows machine here that you see. But that's just the engineering tool. Yeah, so your application would be running on the PLC here. Okay, yeah, that much about the demos. The architecture for the Ethernet IP adapter demo that I just showed you. Again, TI AM64, A53, Linux BSP, Industrial Comms SDK. This time it's the Ethernet IP adapter firmware and an Ethernet IP network. Ethernet IP adapter stack from TI, Phytec Industrial Ethernet SDK that adapts all of this to the Phyboard. And then our custom network, custom Ethernet IP application that handles the I/O, for example. And again, we have two RP message servers for the process data objects so that you can have process data on Linux, and also an RP message server for the non-volatile memory so that we can store all of the Ethernet IP stack data on Linux and don't have to care with separate configuration flashes, for example, or EPROMs. With Ethernet IP, you get an EDS file that needs to match your application, and you use that in the CodeSys PLC, and then you can control your device. Architecture is pretty much the same as before. TI AM64 PRU does all the packet handling, low-level stuff. The R5F runs the actual network Ethernet IP adapter stack. It supports explicit and implicit messaging, LLDP, DLL, DLR, and so on. Again, it is an integrated two-port cut-through switch. It supports quality of service with 4 RX and TX queues, device level ring, time synchronization, link layer discovery protocol, and more. Again, have a look at the TI documentation. The demo for this I've shown you before. The industrial Ethernet SDK for the Phyboard. This is what Nick talked about. That's now available. It is based on TI's Industrial Communications SDK version 11, so really the latest version up on ti.com. It comes with the adaptation of the TI SDK to the Phyboard so that you can use it both on the ports on the Phyboard itself and on the expansion board that you could briefly see in Nick's photos before. It supports all the protocols, EtherCAT, Profinet, and Ethernet IP. And it comes with the sample application for the R5F corp that we provide in source code, so that you can really use that as a starting point for your own development purposes with access to GPIOs and the ADC. And it comes with an example application on Linux that starts and talks to the R5F application and that emulates the non-volatile memory in the Linux file system, and that implements this non-real-time process data on Linux. And it includes a getting started guide. You use the TI Code Composer Studio, that's TI's IDE, Eclipse or Theia. You use TI's sysconfig and Industrial Communications SDK and TI's ARM compiler. You need to be aware of licensing. Phytec's SDK comes with a BSD 3-clause license. TI SDK has its own license, but that is similar permissive. You need additional licenses for the industrial Ethernet technology, like the Beckhoff slave stack code. Typically, you need membership in the relevant technology groups, so ETG for EtherCAT, PROFIBUS for Profinet, and ODVA for Ethernet IP. That's a requirement to use the technology and build sub-devices. About some use cases that are possible with this, you could, for example, build a complex industrial Ethernet device, complex because you are using a Linux processor, so you have something not quite standard, with exchangeable protocol support. Multiple protocols can be supported with the same hardware simply by exchanging the R5F firmware. We include 3 copies, 3 times the R5F firmware for EtherCAT, Profinet, and Ethernet IP on our Linux. And if we start the EtherCAT application, we have an EtherCAT sub device that talks EtherCAT on the network. If we run the Profinet R5 application, always the same Linux application, we are now a Profinet device in the Profinet network. And with Ethernet IP, we can do pretty much the same. We have our Linux application, the Ethernet IP adapter application, and now we are operating in an Ethernet IP network. I would always use the R5F core for like the real-time process data. Everything that needs to be handled with latencies of 10 microseconds and less is possible with the R5F core. You could even use the PRU. Yeah, you have another PRU subsystem to offload some of the data copying, and that allows you to get latencies well below 1 microsecond down to 100 nanoseconds or less. The AM64 itself supports various I/O, both low and high speed. So you can have all the standard peripherals like SPI, I2C, pulse width modulation, and so on. But you could also have an FPGA connected via PCIe and feed EtherCAT data or Ethernet IP data to your FPGA and back. And you could use the fast serial interface to connect with other TI MCUs that are good in motor control application and so on. You have lots of DNA in the AM64, which helps you offload the copying from the protocol to your I/O, to your peripherals. And you have very good time synchronization support so that you really you get the time synchronized down here to below 100 nanoseconds. And you can really pass that time base, for example, over PCIe to an FPGA. And you always have the A53 cores running Linux with latencies, in our experience, well above 100 microseconds. And you use that for the configuration of your industrial network, for a web server, for diagnosis, for firmware update, for all your connectivity needs, because that is where Linux shines. And for all your mass storage needs, because you can support all the file systems there are in the world, and you can use all the USB sticks there are in the world, which gets difficult with the R5F. Another possible use case would be a converter for industrial Ethernet protocols. You could have a multi-protocol solution like we had before, EtherCAT, Profinet, or Ethernet IP, running on one R5F and one PRU ICSSG. And then you can run our own EtherCAT main device stack on the R5F on another R5F, because you have 4 of those. And you have another ICSSG, or you could use the CPSW, and run your own EtherCAT sub-network that's controlled. Above it's controlled via Profinet or Ethernet IP. And below you're using EtherCAT for your own IOs or for including third-party IOs, whatever. You can implement time synchronization between those networks, because that is something that the AM64 is really good at. And you could use the Linux A53 cores for dynamic configuration, which could become complex if you support third-party I/O down here, for scanning of your subordinate network, for the mapping of the process data, because that is, of course, your job. How do you map EtherCAT to Ethernet IP? And for diagnosis purposes, for example. Another potential use case would be an IoT gateway. We provide I/O data from our industrial Ethernet network or from local I/O in the cloud. We could be active with multiple communication protocols, EtherCAT and Profinet at the same time. Two protocols can run in parallel. And we would use Linux for remote connectivity, remote communication with the cloud via Ethernet or via Wi-Fi connected via SD or PCIe. And Linux would allow you to support all the cloud technologies there are, all the data formats, all the security requirements that you have when talking over the internet to the cloud, firmware update over the air. All of that gets a lot easier if you have a Linux application running beside your real-time application. Also secure boot encryption, certificate management, all these features. That is it from my part of the presentation. Feel free to get in touch with either of us, Nick, Catherine, or me.